Welcome to a walkthrough of the libreriscv hybrid CPU, VPU and GPU. This processor design has some unique features in which we are not using SIMD. We're using vectorization system that can issue polymorphic 64, 32, 16 and 8-bit operations right down to the byte level on the register file. Now, the way that's done is that the operation bit widths are overloaded to indicate that it's still register 1, but that you want multiple arbitrary length 8-bit operations, for example, which will extend over if there's 8 of them, it will go in R1, but then it will go next move on to R2 and R3, etc., etc. So this can be interleaved with operations that are 64-bit in size, but you can still have issues in sequence which are 64-bit, 32, 16 and 8. So that produces some unique challenges. Now, what this proposed scheme does is it also provides register renaming without CAMs and without requiring a separate architectural physical register file subdivision. So initially we looked at the Tomasulo algorithm, and unfortunately it turns out that requires CAMs, and the CAM is on this the reorder buffer destination register number, because you can have multiple entries here pointing to one thing, and you use the one at the top thing which you is in. All right, so this points to here. And this is the instruction order on a cyclic buffer. So that's why you need the CAM, because it's register number is multi-entry here. So here's your reservation stations where you have multiple rows, and it's the multiple rows here which is the very nice feature of the Tomasulo algorithm, which does away with the need for a split architectural register file. You can see the number of physical register entries equals the number of architectural register entries, and it's because of these reservation stations with the linker, the reorder buffer. You replace the number of the register with a reorder buffer row entry, which will store the result, and then that gets fed back in and for the common data bus, blah blah blah, etc., etc. The common data bus being the choke point. Now, here instead is a scoreboard matrix system where, again, you can see reservation station table rows, and the register alias table, this tag is equivalent to this entry here, the destination reorder buffer register. Right, but this is not a CAM. It is, however, a multi-bit entry thing. So each of these stores a multi-bit pointer to here. Now, the first step that I worked out, which is described in a separate video, is that instead of having function unit for add and function unit for multiply, you turn this and flatten this table out. Now you only have a 1-bit entry, and you have in here you have a series of 1-bit tags. All right, and I pull the cable over here, and that's what's done here. So I cross that entry out, so this is why you don't have a 4x4 on here and a 4x 4x8 on here. So this this and this goes to there to create that. Yeah. All right. Now this does not mean that you have two adder operations. What you can do is you can have a single adder, pipelined adder, and then it produces a result and it farms back out to the result destination latches. In the original 6600 algorithm, which you can see in the book The Design of a Computer by James Thornton, which many thanks to him and his wife for making that available online now. You can see that these source and destination, so the source values are latched anyway as part of the thing. So there's no extra, no extra cost by doing these. Just calling these reservation stations. And in the design, which we'll see on the page in a bit, actually what you could do is just have the opcode next to each of these and farm to any operation, pipeline it and decode it and farm it back out to its destination. That's not a problem. So so basically, where this is this tag is a single number, what we've done is simply expanded that out into a mutually exclusive one bit entry, which refers to this, and that becomes this table here. There, that's that's equivalent to the rat table. All right. So, what's the unique bit is that this 64, 32, 16 and 8-bit subdivision. And so what we've done is put multiple entries. So you have function units for 32-bit dedicated 32, 16 and 8-bit. I deliberately put more of the ones on the 8-bit than the 16 and 32 because you will be allocating far more 8-bit operations. And so we also have a level of indirection on the registers. So rather than here, you have the function units followed by the number of registers. What we would need to do, if copying that, would be to have R1, R2, R3, R4, 5, 6, blah blah blah, R1 high, R1 low, R2 high, R3 to R2 low, R3 high of a thing, and then the 8-bit, and that's going to be completely insane and unmanageable. So instead what we've done is added a level of indirection on here, and that reduces the number of the size of this matrix to a sane level, without everything. We still get the 32-bit, 16 and 8-bit operations. Now, what happens is that, and I've only done 32-bit, but obviously you would expand out another level 64. When a reservation is made here, then the function unit 1 requires register 1. It also prevents, in a cascade fashion, the 16-bit high and 16-bit low from firing, and also prevents the 4 8-bit values, byte 1, byte 3, 2, 1 and 0. Now, what is particularly fascinating is if it goes the other way round, it does not reserve these values. So whilst the high byte, I know it doesn't reserve that one either, so whilst the high byte is reserved here, it will also cascade reserve the 16-bit and the 32-bit. The low 16 bits will remain empty, which will also leave the low 8-bit read entries thing, and byte 2 will not be reserved either. So let's do another example. Let's say the first operation reserves byte 3 in function unit 1 in register 1. That will cascade reserve this 16-bit and the 32 and the 36-bit and the 32-bit here. Then the second operation will be a 16-bit one, again for register 1, on the low 16 bits. That will cascade down, reserve bytes 1 and byte 0, but it will leave this one free. So that is what I was saying, and then you can get the third operation on that. Now, remember that you can have multiple function units, all right? So there could be operations which require, this 16-bit and then that 16-bit, or that's this 16-bit followed by the 32-bit. What will happen is, under the renaming scheme, the register renaming, you will just go on to function unit 2, and there will be a dependency between function unit 1 32-bit and function 2 8-bit. It's on the same register 1, or what will ultimately be the same register 1. What is also nice is that each of these, when it comes to writing the register, these are your byte select lines. Right? And then these are your word select lines, so that would be the 2 by 2 bytes, etc. And the thing, wrong one. These will be these are your word select lines, high word, low word, which will activate two things. And likewise, when you get to the 32-bit, it will do the whole lot, and 64-bit, it will do the entire register bank. So, unfortunately, we do need this massive matrix of 32-bit op function units to 16-bit function units to 8-bit function unit dependencies. I'm sorry I drew it. Let's move that lot out of the way. And the reason is very simple, that you may have, and may genuinely have, some 8-bit operations which critically depend on 32-bit or 16 and the other way around. So consequently you need that the standard secondary function unit to function unit table, which is not properly made mention of in the standard academic literature, because the academic literature is based on the patent, not on studying the original CDC 6600 design. So this is a fourth table with a level of indirection that goes on onto the system, and that it provides, as mentioned at the beginning, to summarize, it provides vectorization front end on what would otherwise need to be require assembly operations. So you get the advantages of vectorization. If you're not familiar with that, look up SIMD considered harmful on Google. You'll find that. There are no cams. There is register renaming built in without requiring a separate physical register file, architectural file, because it is the function units that store the values in latches, not flip-flops. If you look at the original CDC 6600, you can use latches, which are a lot more efficient. Thank you very much.